Greetings. Welcome to Electronics 2. This is lecture number 25 and I am Razavi. Today we will finish up our study of frequency response in various circuits and conclude with some observations about what we have learned. So we will go back to the output impedance of followers from last time and finish up that topic, and then we will look at the frequency response of cascodes and differential pairs. Again, these are circuits that we have seen before at low frequencies. And then we will look at what we call the transit frequency, which is a sort of an interesting and useful concept. All right, so just a quick review of what we saw last time. We looked at the frequency response of emitter followers and source followers. We derived the input-output transfer function. It was not particularly useful. We also looked at the input capacitance of the circuit resulting from only CPi or CGS. And we saw that the input capacitance is actually quite smaller than these values because the emitter is bootstrapped to the base or the source is bootstrapped to the gate. And by that we mean if the base goes up and down, the emitter also goes up and down almost equally. So this capacitance voltage doesn't need to change, which means we don't need to deliver charge to the capacitance, which means the input capacitance is lower than just CPi or CGS by this factor. All right, then we looked at the output impedance of the circuit. We constructed the equivalent circuit and found Vx over Ix like so. I made a mistake last time, so please make that correction. Here it should be RG CGS-S, not GM RGS. Okay, so this is the correct expression. So today we want to spend some time on this and understand what this means. Why are we studying the output impedance suddenly? Because this has some interesting repercussions. Okay, well, this is a complex number, so we can plot its magnitude as a function of frequency, right? Just the way we did it for transfer functions. So what I need to do is just find the zero and the pole frequencies and then use Bode's rules. All right, so the zero is given by minus 1 over RG CGS by setting this to 0. And the pole is given by minus 1 over, or rather minus GM, the GM over CGS, right? So that's the pole and that's the 0. Okay, so let's plot the magnitude of Z out, right? The Z out here. So Bode says that it's very easy. You just start at low frequencies and we go up, and every time we reach a 0, the slope deflects up by 20 dB per decade. Every time we reach a pole, it deflects down by 20 dB per decade, right? So that should be straightforward. Let's do that. So this is the magnitude of Z out as a function of frequency. And I just have to identify the zero frequency and the pole frequency, right? Okay, so I need to consider two cases because I don't know which one of these is closer to the origin, which one has a smaller absolute value. So we'll consider two cases. Case one. Okay, so you see here we have 1 over Rg CGS. Here we have Gm over CGS, right? So in case one, I'm assuming that Gm is less than 1 over Rg. Okay. All right. So that means that because this is less than this, the zero occurs because Gm is less than 1 over Rg. The zero occurs at a higher frequency than the pole. Right. The pole frequency is lower. So here's the pole frequency, Gm over CGS. Here's the zero frequency, 1 over Rg CGS. All right. When omega is 0, how much is the output impedance? Well, omega is 0 means S is 0, right? So just have 1 over Gm. As expected, right? The output impedance of the circuit at low frequency is 1 over Gm. Okay. Now, because Gm is less than 1 over Rg, 1 over Gm is higher than Rg, right? Okay, so at low frequency, the output impedance is 1 over Gm. We reach the pole, we go down at 20 dB per decade, we reach the zero, we flatten out. So that's the response of the output impedance as a function of frequency. Let's consider case number 2. Case number 2, the other way around. So Gm is greater than 1 over Rg. Okay, so everything gets swapped. Here we go. We have omega, magnitude of Z out. So we still have 1 over Gm and Rg, except that 1 over Gm is now less than Rg. So 1 over Gm is here. Rg is here. At omega equals 0, the output impedance of the source follower is 1 over Gm. So here's 1 over Gm. And we have, because Gm is greater, the pole frequency is higher than the zero frequency. So we have 1 over Rg CGS. Then we have Gm over CGS. Okay. All right, so we start at 1 over Gm, go all the way to the pole, to the zero. Body says now go up at 20 dB per decade, and then we reach the pole, and then we flatten out. Okay, so we see two different types of behavior depending on the relative values of Gm and 1 over Rg. Which one of these is more likely to happen? Well, in practice, we would like the source follower to act as a buffer, right? So here's the situation. Remember I showed you this before? We have like a common source amplifier, and we need to drive a load. And if we just connect this to this, like a speaker, the gain of the source follower drops considerably. So we place a buffer here, and that buffer could be a source follower, right? So the idea is that the output impedance of this buffer is much lower than the impedance that the original amplifier presented. And that's what we would call Rg. So we want the output impedance of the buffer to be less than the output impedance of the original circuit. Otherwise, there's no reason to put a buffer here, right? Okay, so case number 2 is a more realistic case. And it's also a more interesting case. Because if we examine the behavior of this impedance from here to here, we see something interesting, right? What is going on here? The impedance at the output of the source follower is going up with frequency. Does that remind us of any component from basic circuit theory that has a similar behavior? Yes, inductors, right? So we know that if we have an inductor, of L1, then the impedance of this inductor is L1 times S. So the magnitude of this impedance would be L1 times omega. So indeed, the impedance of an inductor goes up with frequency. So the key point here is that the output impedance of the source follower acts as an inductance in this frequency range. So let's highlight that using this color. So we say inductive behavior. And that's the reason we studied this output impedance. Now, is that a good thing or a bad thing? Well, it depends on the application. In some cases, actually, we benefit from this inductive behavior. And in fact, using that, we can build what we call active inductors. An active inductor means a circuit that looks like an inductance, but doesn't use a physical inductor in it. It uses transistors to emulate the behavior of an inductor. And that's beyond the scope of this course, but this is sometimes used in advanced analog and high-speed circuits. All right, so that is the study of the output impedance of the source follower. The emitter follower behaves more or less the same way. Now we're going to look at the frequency response of Cascodes. Okay, so let me go to a different page and look at the response of the Cascode structure. So, frequency response of Cascodes. Let's begin with the bipolar Cascode. All right, and here's our circuit. There's a bias voltage here, collector resistor. This is the output node. Call this Q1, Q2. Okay? All right. So again, this resistor is not something that we add deliberately. This models the output resistance of the stage before the circuit. All right, so we like the Cascode topology because it provides a higher gain, it provides a higher output impedance. But it also has another beautiful result, beautiful property, that was discovered actually well before these things, in the 1930s, maybe 40s, in fact, in conjunction with Miller effect. So what we will see is that the Cascode topology has less Miller multiplication in it than the non-Cascode topology, meaning just the basic emitter, common emitter stage. All right, but one at a time. Okay, so each transistor contributes 3 capacitances. So we're going to draw all the capacitances in the circuit and then see which ones can be combined or dropped out, etc. And then we try to analyze the circuit. All right, so we will get there shortly. But before we do that, I want to just make a simple observation about the low frequency behavior of the circuit. All right, so this is something we did not study before because we didn't really need it at the time, but now we need it. All right, here's the point that I want to show you. Let's consider this node, call it A, and this node B. So the question is, how much is the voltage gain from this node to this node? All right. Previously, we didn't look at it because the output of interest to us was here, not here. But we need this, so let's try to find that voltage gain. So here's the voltage gain. Let's call it AV, V, B over VA. Okay. How much is that? This voltage gain. This is not the overall voltage gain. It's just from here to here. Okay, well, if I look at Q1 very carefully, I see that VA is applied at the base, the emitter is AC grounded, and the output of interest is at the collector. So Q1 acts as a common emitter stage. So the gain is simply given by minus GM of this device times the resistance that we see at this collector, right? So let's assume that the early effect is neglected. That means that the output resistance of this transistor is infinite, so we don't have to worry about that. What remains is what impedance do I see looking up here? So I have Q2, the base is at AC ground, and I'm looking at the emitters, into the emitters. So from electronics 1, remember that that impedance is just 1 over GM of the transistors. So this would be 1 over GM2. So that's all. So this is multiplied by 1 over GM2. So take a moment to digest this. And also remember that for a bipolar transistor, the transconductance can be expressed in terms of the bias current. So what we have is for GM1, so minus, we have IC1 over VT, right? That's the equation for the transconductance of a bipolar device in terms of the collector current, the bias current. And similarly for Q2. How are IC1 and IC2 related? Well, they're approximately equal, right? The bias current is the same approximately, so everything cancels out, and we see that the gain is equal to -1. So the voltage gain from node A to node B is approximately equal to -1. All right, so remember that. We're going to go now and look at the capacitances. All right, so I'm going to drop all the capacitances into the circuit. So here we go. We have C pi 1, then we have C mu 1, then we have a collector substrate capacitance, CCS1. 3 capacitors for Q1. For Q2, same thing. So we have C pi 2, C mu 1, C mu 2, and then CCS2. Okay? All right. Which one of these caps can be combined? CCS1 goes from B to ground. C pi 2 goes from B to ground. So these two are combined. At the output node, C mu 2 goes to AC ground because VB doesn't change with time. CCS2 also goes to AC ground. So these two add 2. Okay, so let me change the color and write those out. So what I see is that I can cross this out and write it here, C pi 2. I can cross this out and write it here, C mu 2. That's great. So we got rid of 2 capacitors. Now the circuit is simpler. Okay, I would like to determine the frequency response by finding the poles by inspection. If I have the poles, then I can use Bode's plots to figure out what the frequency response looks like. All right, so then for every node, I need to find the capacitance to AC ground and the resistance to AC ground. The difficulty relates to node A and node B because we have this capacitance going between the two. As we saw in our examples before, C mu 1 does experience Miller multiplication. So we would like to decompose C mu 1 into 2 grounded capacitors. So let's do that. We can do that, right? So let's cross C mu 1 out and put it right here as a grounded capacitor. How much is that? C mu 1. Miller says take the capacitor, multiply it by 1 minus AV. Right? AV is the voltage gain from here to here. Remember we call this node P, node Q. So now we call it A and B. How much is AV? We just found it, right? So that's just 2 C mu 1. Okay. Now, when we decompose this capacitor, we have one at the input, one at the output. There's another one that goes from here to ground. And how much is that? So Miller says that would be C mu 1 times 1 minus 1 over AV. Interestingly, in this case, AV is minus 1, so this also comes out to be 2 C mu 1. All right? So methodically and intuitively, we try to simplify the circuit one step at a time and get to a point where we can analyze it quickly. All right, so now as you can see, I have only capacitance from node A to ground and some resistance, only capacitance from node B to ground and some resistance, and similarly at the output node. So if you have difficulty visualizing what's going on here, pause this video and redraw the circuit with these caps gone, this is gone, this is gone, this is gone, and just these caps present, right? Just to see what's going on. Okay, so let's write out all the poles. We have one pole at this node, omega PA. How much is that pole? Well, we said what we do is we find the resistance to AC ground. We have RB going this way to AC ground because the independent source is set to 0. We have R pi going to AC ground. So these are in parallel. So we have RB in parallel with R pi times the total capacitance that we have to ground, C pi 1 plus 2 C mu 1. This cap plus this cap. So C pi 1 plus 2 C mu 1. All right. Okay. Let's go to node B now. Similar story, right? At node B, I have to find the resistance, and then I have to find the capacitance. So omega PB, the pole associated with node B, is given by the resistance. How much resistance do we have at this node? Remember, we saw 1 over GM2 before, so that's the resistance, right, to AC ground. So 1 over GM2, and then how much capacitance? Well, we got this, and we got this. So we have CCS1 plus C pi 2 plus 2 C mu 1. All right. And finally, the output node. At the output node, I have a resistance of RC, and the capacitance is just these two. So I can say omega P out is equal to 1 over RC times CCS2 plus C mu 2. So that is the output pole. All right, so you see that we started with a relatively complex circuit, lots of capacitances and 2 transistors. So if you wanted to draw the small signal model of the circuit, it would be pretty overwhelming. But knowing what we have developed so far, and with the intuition that we have, we can methodically break down the circuit into smaller pieces, into simplified pieces, and then come up with these approximations for the pole frequencies, right? All right, so you may ask, we have 3 poles, which one tends to be the limiting factor as far as the bandwidth is concerned? Well, typically, the pole at this node, which we call the Cascode node, is very high. So typically, that frequency is not the limiting factor. So this would be this one here, right? So typically, very high. So typically we end up with the input pole at node A and the output pole as the 2 candidates that might limit the speed or the bandwidth of the circuit. Okay? And in most cases it's the output node that limits the bandwidth, but there could be some exceptions where the input pole limits the bandwidth. All right. So we should repeat all of this for the MOS cascode. By the way, I also wanted to emphasize that, as you can see, if I compare this situation, so before we go to the MOS version, compare with simple common emitter stage. So we see that here the Miller multiplication of C mu is much higher, right? So here we have C mu times 1 plus GMRC as call it C1, right? To ground, or C in to ground. So when I decompose this capacitor into two, the one at the input is C mu times 1 plus GMRC. So compare this number with this number, right? So if the gain of the circuit is 10, here we are multiplying C mu by a factor of 11, whereas here we are multiplying it by a factor of 2. So this was the original motivation for using the Cascode topology, because people realized that the capacitance of the amplifying device from here to here is not multiplied up that much. It's only multiplied by a factor of 2. Whereas if we don't have the Cascode structure, this capacitance of this device is multiplied by large numbers. So the Cascode topology does not have as much Miller multiplication as the simple common emitter topology. All right, now we go to the MOS version. The MOS version is very similar, so I'll just skip all of that. You have all the capacitances, everything here. Of course, this is now called CGS1, not CPi1. But there is also very similar, so we won't really deal with those that much. All these equations are approximately correct there. Of course, we don't have R pi for a MOSFET, so that goes to infinity. But everything else remains, so it's very similar to what we have derived. All right? Okay, so let's go to the frequency response of the differential pair. This is pretty easy based on what we have learned about differential pairs before. So again, we can look at the MOS version or a bipolar version. It's the same story. So here's the MOS version. So I'm including these resistances here again because they represent what comes before the circuit. So we have RG. So we have V in 1, V in 2, RD, and then a tail current ISS, and a tail node P. So if you recall, we analyzed the differential behavior of the circuit, the differential small signal voltage gain, by realizing that when the inputs are completely differential and small, node P does not change its voltage, so it can be considered AC ground. And once we consider this AC ground, the circuit breaks into two halves. So we just analyzed one half and found Vx over V in 1. And then we said, well, Vx over V in 1 for one half is actually the same as Vx minus Vy over V in 1 minus V in 2 for the entire circuit. So one half of the circuit looks like this. Right? So this is V in 1 here, and this is Vx here. That's what we did before. We recognized that node P is AC ground. We considered half of the circuit. We found the gain for half of the circuit. And we said the gain of half of the circuit is actually the same as the differential gain of the entire circuit. This was done at low frequencies. So now we go ahead and include the capacitances of the transistors and see what happens, right? Okay, so let's go ahead and drop all the capacitors in. So we have CGS1, M1 and M2, CGS2, then there's a capacitance from the source to ground. So CSB1, CSB2, then there's CGD1, CGD1, CGD2, CGD2, and there are two caps from the drains to AC ground, right, to the substrate. So this one and this one, I will just write here CDB. One is CDB1, one is CDB2. Okay, I don't have room, so just CDB. All right, each MOSFET contributes 4 capacitances. That's what we have. All right, again, assume that the inputs are differential and small. So node P is AC ground. Okay, so AC ground. Which one of these capacitors go out of the picture? This one and this one, right? Because they go from AC ground to ground, so they don't play a role anymore. So those are gone. So we cross these out. And then we just have, now we go to the half circuit, right? Because this is AC ground, I can just consider 1/2. In the half circuit, I have CGS1, then CGD1, and then CDB1, right? Does that circuit look familiar? Yes, that is the common source amplifier whose frequency response we calculated before. We used the Miller approximation first, and then we used the exact transfer function. We looked at the dominant pole approximation, all of those things. So everything that we have discovered about this amplifier applies to this amplifier as well, as far as the differential transfer function is concerned. All right, so that's why we don't have to study this in detail again. Okay, so we just take the transfer function we had here and use it for this guy as well. All right. Okay, so that's easy enough. All right, the last topic I wanted to go over here today is the notion of the transit frequency. So let's talk about that. The transit frequency, which we denote that by F sub t. Lowercase f, uppercase t. Okay, so what does that mean? Well, if I give you a transistor, could be MOS or could be bipolar, right? And I say, how good is the transistor in terms of high frequency operation? What would you say? Well, you would say, well, I have to look at all the capacitances, right? So we have C pi, and then other stuff. We have CGS, and then other stuff. So it depends on these values. I can't just say how good the device is. But we are still looking for a single number, a figure of merit that would tell us how good a transistor is, or at least would allow us to compare one bipolar transistor with another one. So if I give you two bipolar devices and I say which one is better in terms of high frequency operation, maybe we can find a single figure of merit that will reveal that information. And that figure of merit is called the FT. So let me define what we mean by the FT. So this is the frequency at which the current gain of the device drops to 1. Okay? It's strange that this is called the current gain, right? We're looking at the current gain of the device. So take a moment and write this down, and then we'll see what this all means. All right, so we introduced the bipolar and MOS devices really as voltage-driven devices in Electronics 1. So it's a little strange that we're looking at the current gain of the device, right, rather than GM, the transconductance. But that's okay. This still gives us some number to work with, and we will use that. So what this means is that I would like to apply an AC current to the input, to the base, while the emitter is grounded, or to the gate while the source is grounded. It's a sinusoidal current source, small in value, and I keep increasing the frequency of the sinusoid. And I keep monitoring the current gain of this device. The AC current over here divided by the AC current that we apply. And at some point, the device runs out of juice. So the current gain drops to 1. And at that frequency is called the transit frequency. Okay? So let's build a little setup to do that. For either of these, it's the same thing. So here we go. First, I need to bias this device. So I'm not showing the bias circuitry. Let's say it is biased properly. And I have a battery here. So VB, some voltage, let's say 1 volt. And this is biased, so biasing not shown. I want to make sure that you remember this, biasing not shown. And now I come along and I inject a sinusoidal small signal current into the base. And I call this I in. So I in might be a current that goes up and down by maybe 1 microamp, 2 microamps or something, right? And I am interested in this current here, the AC current, called I out. So this is a transfer function, right? A sinusoidal input going here, a sinusoidal output appearing here. So I out over I in is a transfer function. So I can go ahead and say I out over I in, which is a transfer function, evaluated when S is replaced with j omega. The magnitude of that at some omega, at some input frequency, will drop to 1. So this will drop to 1, right? So that frequency will be called omega t, and omega t is just 2 pi ft. So you can call this the transit frequency or this. They differ by a factor of 2 pi, right? This is radians per second. This is hertz. Okay, so this is the setup that we would construct, for example, in simulations with proper biasing. And then we keep increasing the frequency of this one. We can plot this as a function of frequency, right? So we plot the magnitude of I out over I in. This would be a simple AC simulation in for example, SPICE. And then what we'll see is that it goes like this. At some point, it becomes equal to 1, right? And that would be the transit frequency omega t. Okay, so can we derive an equation for omega t or ft in terms of the device parameters? We should be able to do that, right? So let's go ahead and do that. Let me see if I can do it right here. So I will go and I will consider only C pi. I will neglect C mu. We can do it more precisely with C mu included, but for simplicity, we just assume there's C pi. Okay, C pi is the dominant capacitance anyway. All right, so I need to find I out over I in. What does this I in do? This I in is injected into some sort of impedance and generates a voltage. That voltage multiplied by Gm gives us a current. So that's how we would find the output current, right? Okay, so from a small signal perspective, this is what we have. We have I in going into well, C pi, then R pi, and then on this side we have Gm V pi, and then this goes to AC ground, and I out is this current. Is that clear? I'm just drawing the small signal model of this whole circuit. Okay, so we have C pi here and R pi in parallel, and then V pi is here. Okay, how much is V pi? V pi is this current multiplied by this impedance, right? A resistor in parallel with a capacitor. So V pi would be equal to, how do you write the parallel combination of a resistor and a capacitor? Should be pretty easy, right? Here's what we get. R pi divided by R pi C pi S plus 1. Is that clear? Because what you would write is R pi in parallel with 1 over C pi S. When you have to multiply and divide and so forth, and that's what you get. This equation is this parallel impedance. You can see that S equals 0 is R pi, as expected, because at S equals 0, the capacitor is open. I in is multiplied by this impedance to give us V pi. So I will multiply this by I in, and that gives me V pi. V pi is multiplied by Gm to give me this current. So I multiply this by Gm, and that gives me I out. Okay, so we found I out over I in, right? And all I need to do is find the magnitude of this transfer function, set it equal to 1, and then find the omega value that will give me that result, right? Okay, so not a problem. I need to carry this over to the next slide and then work with it, okay? So GMR pi over this. If I divide by I in, I have I out over I in is equal to GM R pi over R pi C pi S plus 1. So remember that. Let's go to the next slide. Okay, so I out over I in is equal to GM R pi C pi S plus 1. All right, okay. How much is GM R pi? Do you remember from Electronics 1? Call that beta, right? That's the current gain, so 100 or something. Okay, so I will need to write I out over I in S equals J omega, right, is equal to beta. Now for convenience, I'm going to write the square of this. So that's beta squared here. And then that would be the imaginary part squared plus the real part squared, right? So that's RP squared, C pi squared, omega squared plus 1. You can call this omega t, because we are looking for the transit frequency if this is equal to 1. If the magnitude is equal to 1, the magnitude squared is also equal to 1. Okay, so what do I get? I'm looking for omega t, right? So I have beta squared minus 1 is equal to R pi squared, C pi squared, omega squared. Beta squared is definitely much greater than 1, so that goes away. Take the square root of both sides. We have omega t is equal to beta over R pi C pi. How much is R pi over beta? That's 1 over Gm, right? So then this is Gm over C pi. Okay, so that is the equation that we need to remember. For a MOSFET, it's similar. So for a MOSFET, omega t is equal to Gm over CGS. Or if you like, you can write Ft is equal to Gm over 2 pi CGS. So that's a nice little nifty equation that we should keep in mind when we are considering the Ft of transistors. So what kind of Ft's do we have these days for these transistors? Well, for integrated devices, the Ft's are quite high. So for integrated circuits. So we have a CMOS technology or bipolar technology. The devices are, the FTs are in the range of several hundred gigahertz. Okay? So they're quite high. If you buy a discrete transistor, like a discrete bipolar transistor, it might be 5 gigahertz, 10 gigahertz, something like that. Okay. All right. So that's good. These equations also help us decide how we can maximize the FT of a device. So let's talk about that example. Let's see, how do we maximize FT? Well, for a MOS device, I'm going to write it like this: 2 mu n C ox W over L ID 2 pi CGS. So, if I really want to maximize FT, my best bet is to increase the drain current, the bias current of the device. Not W over L, because as I increase W over L, the capacitances of the device also increase. So that's not the proper approach to do it, right? So to maximize the FT of a device, we would try to maximize the bias current. This is for MOSFETs, not for bipolar devices. So that's one technique that we try to use. Of course, there are trade-offs in that. As usual, we have a trade-off between speed and power consumption and gain and everything else. But that's something that we could try to do by maximizing the drain current so that CGS is constant. We can just keep increasing VGS and the current. Okay, this concludes this lecture. I will see you next time.